So the system we had was to take the difference between the input and divided version of the output, integrate it and drive the output. This we know in steady state drives the output to k times the input. Okay. So if you have a stationary or DC input, the output will be exactly k times the input. And if the input is varying, depending on the frequency, it can be nearly k times the input, or as the frequency is increased, it can be very different from that. Okay. The loop gain, which is basically the gain around the loop, can be found by breaking the loop. Since this is an ideal loop, we can break it anywhere. And we set the input to 0, and you break it here, apply a test quantity here, let's say V test, and see what comes back. Okay. So VFB by V test is omega u by Ks. Okay. So the Bode plot of loop gain, the magnitude plot looks like this, where the slope is minus 20 dB per decade. And it crosses unity at omega u by k. That is, the unity loop gain frequency is the unity gain frequency of the integrator that we have used divided by the feedback factor. Okay. So now for an ideal feedback system, we would want the loop gain to be large. So this is the region of large loop gain, and this is the region of small loop gain. Now as an approximation, we can take the unity loop gain frequency to be the point that divides the region of large loop gain and the region of small loop gain. Okay. So roughly speaking, below this we get ideal behavior, and above this we get non-ideal behavior. Okay. And that is reflected in the closed loop response. What is the closed loop response of this? This being the input and this being the output. What's the transfer function? We evaluated this, right, several times. So k by 1 plus s, and the pole is at omega u by k. Okay. So it has a gain of k up to a frequency of omega u by k, and after that it follows the loop gain curve, which is at minus 20 dB per decade. Now of course this is correct in a Bode plot sense. We know that this is an approximation. In reality, it does drop to 3 dB, right? At omega u by k, the gain is minus 3 dB. I mean, whatever the gain is, whatever the DC gain is, that minus 3 dB. Okay. So this is the significance of loop gain. I mean, loop gain makes the large loop gain makes the circuit behave ideally. Okay. And the unity loop gain frequency is another crucial quantity in the analysis of feedback circuits. So if you want to make the circuit behave ideally for a broader range of frequencies, you have to increase the unity loop gain frequency. Okay. So last time I said you have to increase the unity gain frequency of the integrator to make it faster, but of course that the behavior also depends on the value k. So it's really the unity loop gain frequency that you have to increase if you want to increase the bandwidth, or basically increase the range of frequencies where the circuit must behave ideally. Okay. Is this clear? So, the unity loop gain frequency is the unity gain frequency of the integrator times or divided by the feedback factor. Okay. Now, the thing to notice in this particular case, the closed loop gain was equal to the feedback factor K, but that's not always the case. That depends on where you apply the input and where you take the output from. But the loop gain doesn't depend on any of those things. It only depends on the structure of the loop. And roughly speaking, you have ideal behavior for omega u less than omega u loop and non-ideal for omega u greater than omega u loop. Okay. So, this is we have completed the analysis of the basic feedback loop with one integrator. It gives you in steady state ideal output, and when you have time varying inputs or sinusoidal inputs of various frequencies, for a certain range of frequencies it gives you the close to the ideal output, and beyond a certain value the output becomes non-ideal. Okay. This is in general the property of every feedback circuit, and the frequency that and the quantity that decides where the circuit switches from being more or less ideal to becoming non-ideal is the unity loop gain frequency. Okay. So that's the analysis of the ideal loop. So just to remind you of some things, the closed loop transfer function is this. Okay. So now the question is, can we even implement this loop correctly? I mean, ideally. So we said that essentially we started off saying to drive the output to a certain value, we take the difference between the input and some ratio of the output and integrate it and drive the output. So what are all the non-idealities that can come up? So can I, if I want to make an amplifier, can I go and make this system? Exactly. Or is there something that I can't really realize? You can't make the integrator. Okay, why not? Can't have infinite DC gain. Okay, that is one thing. Then what else can be a possibility? That's true. Actually, if you feed a DC, if you feed DC to an integrator, the output will keep ramping up, and if you wait infinitely long, it will reach infinity. But in reality, whatever circuit you make to realize an integrator, the output will not reach infinity. It will go and reach some particular multiple of the output. Okay, and that multiple may be very large, but it will not be infinite in general. So that's one of the non-idealities. What else can there be? So this is a system with a single pole at the origin. That's it. But you can have additional poles and additional zeros also. So generally you will have at least one additional pole. Okay. So that's those are the main non-idealities. That ideally this is a system with the pole at the origin. Now non-infinite DC gain also means that the pole is shifted away from the origin, right? So the pole will not be exactly at the origin, and also that will not be the only pole. There can be other poles. Okay. Let's see the effect of those things. As before, just to get some feel for what's happening, we'll do the time domain analysis first and then go to frequency domain. Now, time domain analysis, we won't do it completely and it's not very accurate or anything, but it's just to get an idea of what's going on. Right? So, as we said, the integrator non-idealities are firstly finite DC gain. What does this mean? That if you have DC input to an integrator, ideally it will go off towards infinity. Okay. And what will be the slope? if the DC input is some Vx, it will be omega u times Vx. Okay. So what happens in a non-ideal situation, in a real situation? It will start off with a slope of omega u Vx, but the slope will keep on reducing and it will reach some multiple of Vx. It won't go off to infinity. Okay. And the steady state value of the integrator output is known as, it will be A naught times Vx, where A naught is the DC gain of the integrator. Okay. So, and this A naught can be small or large. You can make it larger and larger, but you can't go to infinity. So, what's the effect of this? What is the effect of this? Okay, now we have said, firstly, let me just tell you why this happens. How would you accomplish integration in a circuit? Where do you find an integrating function? Integration with respect to time? In a capacitor or an inductor, and we generally most frequently use capacitors. So, what does the capacitor integrate? It integrates a current to give you the voltage, right? So, if you feed in a current source, it will keep on integrating the current. Now, why does the imperfection come in? So, you can't make an ideal current source. It will always have some output resistance. Okay. So, when it reaches steady state, all of the current will be flowing through the resistor, not through the capacitor. So, the integration stops. That's the non-ideality in an integrator. Okay. We'll see the details of it when we make more or less complicated circuits. We'll see where it comes from. But in general, you get integration by forcing a current through a capacitor, but the forcing current source will not be ideal. It will have a finite output resistance. Because of that, the steady state output, in steady state, the current will flow through the resistor, not the capacitor. Okay. So, the integration stops. So, fine. Now, we have established that an integrator doesn't really integrate to infinity. It has some finite DC gain. Okay. DC gain means that if you hold the input for a long time, you see the output, the ratio of output to input is the DC gain. In this case, it is A naught. So, what's the effect of this? Should I be even worried about this? What happens to the feedback system because of the finite DC gain of the integrator? What's that? There will be an error. That's correct. So, again, if we go back to our basic reasoning, we said that we drive the output with an integrator, and what it integrates is the difference between the input and the scaled value of the output. Okay. Now, when did we say steady state is reached? We said that steady state is reached when it stops integrating. That is when the output is constant. Okay. The output is constant means the input is 0. That means the quantity here is V naught divided by K. Okay. Now, clearly that cannot be the case because with finite DC gain, you need to, when steady state is reached, the output is constant, the input has to be that divided by A naught. So, there has to be some difference between the input and the fedback quantity. Okay. So, with an ideal integrator, that difference was 0, the steady state difference between the input and the fedback quantity. With an integrator whose DC gain is finite, the difference is not 0. Okay. So, this is not the equation that describes the integrator. So, if you write the transfer function with the finite DC gain, what we will say is, so this is the ideal transfer function omega u by S. Okay. We will also have this additional term. Okay. So, if I didn't have this term, the DC gain would be infinite and the pole is at the origin. Okay. Now, with that term, the pole has shifted away from the origin and the DC gain is A naught. Is this clear? So this is the transfer function. I mean, normally it may be written in a different way. Okay. So the pole is at the unity gain frequency divided by A naught. Pole is at omega u by A naught instead of the origin. So clearly this difference is non-zero in steady state. So there will be a steady state error in the output. Okay. So that's the effect of finite DC gain. Now depending on how much error you are willing to tolerate, the DC gain needs to be appropriately large or small. Okay. A naught and 1 by k. No, this is just the this is the transfer function of the integrator by itself. Okay, or what we thought was the integrator. This is not the transfer function of the overall system. Okay, so k is not yet here. So this is simply the transfer function of this. Okay, so we will calculate the overall transfer function. Okay, this VID, what I meant here was this quantity is VID. Okay. So what is V naught by Vi? So this is one form to write it, right? So what is H? What is the value of H? This is in the standard feedback notation where J is the forward path and H is the feedback path. Okay. What is H in our case? 1 by k. So this is k. And what is this quantity? So I said, what is GH? So 1 by k, and I'll use this form, S by omega u plus 1 by A naught. Okay. So 1 over GH can be conveniently written as okay. So what is the DC gain? What is the DC gain of the closed loop system? K by 1 plus K by A naught. So it is different from K, and how much different it is depends on the ratio K by A naught. So clearly, if you increase the DC gain value A naught, you will have close to ideal performance, right? So if A naught tends to infinity, it should be K. That's what we see here also. And where is the pole? Or the bandwidth of the system, what is that? Huh? So, what's that, omega u? So it's basically where this is where the bandwidth is, right? When the magnitude of the denominator becomes square root of 2. Is that correct? So what is that? Sorry, this times omega, right? Yeah, this times omega square. This is the bandwidth. So the bandwidth is omega u by k 1 plus k by A naught. So it's approximately omega u by k. we assume that we are dealing with a situation where k by a naught is a small number or a naught by k is a large number. So as far as the bandwidth is concerned, there is a shift in bandwidth, but it's not very significant for our purposes. Okay. Now, what is the DC loop gain of the system? A naught by k. So again, you see that loop gain appears in the performance equation. So the DC gain is k divided by 1 plus k by a naught. So if the DC loop gain is very large, then it will be close to the ideal transfer function. If the DC loop gain is small, it becomes non-ideal. Okay. So this again shows the importance of loop gain. In this case, the main effect is on the DC gain. The bandwidth is slightly affected, but we can ignore that for the most part. Okay. Now, the DC performance is important where you are concerned with where the value settles to, right? We are talking about DC performance or what the output settles to in the long term. Now, depending on the accuracy you want, you have to adjust the value of DC loop gain. Okay. So, for instance, if you want a gain of 10, okay, closed loop gain of 10, and your range is given as, let's say, between 9.99 and 10.01. Okay. So, you are supposed to make an amplifier of gain 10. As engineers, we do know that we can't make exactly 10. So, we give some error specification, and that is 0.01. Okay. So, what is the value of DC loop gain we require to realize something like this? Minimum value of DC loop gain? 100, 10,000, 1,000. What's the answer? What is the answer? 100. Why 100? So, I mean, I just substitute here, right? So, 10, the error because of loop gain is 10 by 1 plus k by a naught. And this should be more than this much, right? So, what is the result? K by a naught is 100. How much is this? 0.001, right? 0.01. Why is this so difficult? 0.001. So, the gain is, the loop gain, minimum loop gain you need is 1000. Okay. So, what is the minimum DC gain of the integrator you need? The loop gain is 1000. What's the DC gain of the integrator? That is the closed loop gain times the loop gain. So, that is 10,000. So, you need a minimum loop gain of 1000. Okay. So, you can see the error is 0.01, right? 0.01 divided by 10 is 0.001. So, the relative error in the DC gain is nothing but the reciprocal of the loop gain. So, if the relative error has to be 0.001, the loop gain has to be 1 over that, which is 1000. Okay. For this example, it is more than 1000. So, depending on your application, it can be 1000, it can be million, whatever. Okay. So, it does have, the accuracy specification has an influence on the DC loop gain. Okay. Or that's how, when you are making a feedback system, you first of all know that you can't place the pole at the origin, right? It will be somewhere else. And so that means that the DC gain is some finite value. Like how much should it be? 1000 or 10,000 or 1 million? That depends on the accuracy specification. Okay, you don't have to make it arbitrarily large for every case. Okay. Is this clear? The effect of DC loop gain? The integrator will have a finite DC gain, because of which the DC loop gain is finite, because of which the DC gain has an error, and the relative error, that is the error between the relative error between the what you get and what is the ideal required value, that is the reciprocal of the loop gain. Okay, you get k divided by 1 plus k by a naught. The relative error is k by a naught, which is the reciprocal of loop gain. This again is generally true. You have some ideal value and you get something non-ideal. The relative error between the two will be the reciprocal of the loop gain. Okay. So, depending on how much accuracy you are required to design for, you design a certain amount of loop gain. Okay. So, high accuracy means high DC gain. That's the bottom line. Is it okay? So, what else can there be? We said we will have additional poles in the system, right? So, we will take an example where we have one additional pole, and also we take, when we have a certain number of non-idealities, when we have a number of non-idealities, we will analyze the effect of each of them separately, okay? Because when we put everything together, the expressions become too messy and it's hard to get information out of them. So, we will analyze them separately and assume that the effects add up in some way. So, instead of getting just omega u divided by s, I can have additional poles. I will call this P2 because the first pole is at the origin, so that is the second pole. Okay. Now, I can also have additional zeros, we will see the effect of that soon. So, what is the effect of this? How do you know? Well, it could happen perhaps. But firstly, let us just take the performance of the integrator, right. So, again, what happens if I put a DC into an integrator? The output should ramp up like this. Now, with the additional pole, what happens? Okay. So, this is versus T, and I have an input, let us say VDC, or I think I used Vx the last time, Vx, and if I put an input of Vx, I have a ramp of rate omega u times Vx. Now, this was for an ideal integrator. If I just had a transfer function omega u by s. Now, I also have an additional pole in the integrator. What am I going to get as the output? Exponential. So, what way? I mean, is it going to be this, or what? What happens? I mean, exponential is, this is the negative exponential, or this is the positive exponential. What is it going to be? Huh? So, ideally I would have got a ramp. Now, what am I going to get? Ramp? Ramp plus negative exponential. So, let me try to draw that. So, first of all, why do you say ramp plus negative exponential? So, meaning ramp plus something like this. So, the result will be, I mean, here it is constant. Is it going to be like this? First of all, how did you say ramp plus negative exponential? So, the standard way to solve this, I mean, you want to find the step response of this, right? So, you can multiply this by 1 over s and find it, or, I mean, you can basically resolve it into terms which have distinct poles in them, right? So, each pole has a separate term and you add up all the responses. That's how you do it. So, firstly, let's assume that what he said is right, that it's a ramp plus negative exponential. So, this is what we are going to get, right? We have this negative exponential, I mean, exponential with a negative argument, which settles to some constant value. So, if you look in the long term, the ramp is simply offset, right? Now, here it is something else, right? Okay. So, let's say this is the right answer. Is this good or bad? What happens to the feedback system because of this? I mean, is it good, bad, neutral? Something, one of the three has to be right. Huh? It is good. Why? Yeah, that's right. Essentially, we have a quicker feedback. Okay, so it looks like it will be good. So why is it good? Because if you have quicker feedback, that means that it will respond faster. That's the general idea. But let's see if the answer is right. So if I resolve it into two separate terms, what am I going to get? What's the coefficient of here? What's the coefficient here and here? One and so omega u and minus omega u by P2. So I should not add the exponential, I should subtract it. Okay. So in reality, let's see what happens. So this part is the term that we are familiar with. Okay. So this is just a transfer function. We are supposed to find out the step response. So I'll find the step response of this transfer function, step response of this transfer function, and combine them. Okay. What's the step response of the first one? That's what we had all the time. And the slope is omega u times Vx, where Vx is the input voltage. What is the step response of this? Huh? So let's forget the minus sign. We'll later subtract the two. Okay. So this will give me exponential with a negative argument. Okay. Something like this, and it goes as the order e to the minus P2t. What is the slope at the beginning? If the input is a DC of Vx, what is the slope at the beginning of the exponential? Huh? So it is actually omega u times Vx. You evaluate it and see. So if you have 1 over 1 plus s by P2, the step response of this is 1 minus e to the minus P2t. Okay. What is the slope of this? At t equal to 0? P2, right? And you have omega u by P2 on top. So the slope in fact is omega u times. The slope here also is omega u times Vx. Okay. Everything gets scaled by the input, of course. So I should subtract this one from this one. So what am I going to get? So the slope will be initially 0. Okay. And the slope will be 0 because the slopes of the two are the same, and then it builds up and it follows the ramp. Okay. It will be some constant value below the ramp. So it will be parallel to the ramp in the long term. So is this good or bad? So this has introduced a delay, right? So in response to a certain DC, we were getting this ramp. Instead of that, we are getting a delayed ramp, roughly speaking. So this is not a good thing. This will actually make it worse. So the analogy is, let's say you are again driving a car and your aim is to stabilize the speed of the car, but the speedometer gives you the speed, but not the speed now, but maybe from 3 seconds before. So what happens? You will overcorrect, and then you have to undercorrect. I mean, you have to overcorrect on the other side, and so on. So that's what happens. So if you have delay in a feedback loop, you can intuitively figure out that you can get into oscillations, right? Because during the time that there is a delay, you are still getting the information about, you are getting the wrong information. Okay. So you are applying a correction in some direction. Now it can have overshot in that direction, but you don't know that. Now after a certain delay, you get the information that you have overshot. So then you start correcting in the other direction. Okay. So that's what happens here also. And what is the amount of delay? So here, of course, in this part, in the initial part, it is some exponential. So I look away from the exponential, I look in the long term. What is this delay? What is the horizontal displacement between the two curves? Huh? Omega u by P2. The x-axis is time, so it can't be omega u by P2. Huh? 1 by P2. So let's make Vx equal to 1 just for simplicity. Okay. What is the value here? What is the height of this? omega u by P2, right? So that is the vertical displacement between these two curves. And what is the slope? That is omega u. So the horizontal displacement is the vertical displacement divided by the slope. So this is 1 by P2. Is this clear? Is it okay or no? So this part is okay. This is omega u by P2. So essentially it's the step response of this, omega u by P2 times 1 minus e to the minus P2t. So it will settle to omega u by P2. So this part is omega u by P2. Okay. So, and these are all straight lines, and the slope is omega u. Okay. So if the vertical thing is omega u by P2, the horizontal thing is the vertical divided by the slope. So it's 1 by P2. So a pole at a frequency P2 introduces a delay in the ramp response of 1 over P2 seconds. Okay. So that's the effect of the additional pole. So what does it do? If the pole is at a lower frequency, it introduces more delay. So you can intuitively see that it is worse. We'll see the exact effect afterwards. Okay. And what do you think happens if I have additional poles? So it will actually, you can work it out, it will introduce further delays. So roughly speaking, it will be 1 by P2 plus 1 by P3. Okay. So in the long term, of course, here it is some exponential, right? I am talking here about after the response starts looking like a ramp again. Okay. And in fact, you can easily calculate it for either this case, or you take two poles at the same frequency. That is, you take 1 over s plus 1 by 1 plus s by P2 whole square. You calculate it. You do exactly the same thing, right? You split it into quantities with each pole in the denominator, and you find the residues, and from that you can calculate the step response. If you do that, you will see that the delay is, with every pole added, the delay increases. So you can also from this see that if you have more poles, perhaps at the same frequency, then you will also have more delay, and you will end up with a worse negative feedback system. Okay? Is this okay? So the time domain analysis gives you a better intuitive feel for what happens. It looks like it is delaying the feedback, right? So that means that it is probably taking you closer to instability. Okay. Now, what we have established so far is that if the pole is at a lower frequency, it adds more delay, so it's worse. If there are more poles at a given frequency, again, each pole adds additional delay, so that's also worse. Okay. We will do the frequency domain analysis and see where the poles must be. What about zeros? What do you think will happen? Instead of poles, I will have zeros now. What do you think the response is going to look like? No, just the ramp response. Let's forget the closed loop response for now. Huh? It will help. So what will the response look like? Will it start looking like this? So again, we can calculate it quite simply. What's the opinion? I'm not getting answers from most of the people here. What will happen if I have, this is the ideal integrator, additionally I will have a 0. What is the ramp response? The ideal ramp response again is, for an input Vx, for a DC input Vx, it's a line of slope omega u times Vx. What am I going to get with the 0? Yeah, so this is, again, it's even easier to calculate, right? It's omega u by s plus omega u by z1. Now, is z1 necessarily negative or positive? It can be anything. For the pole, of course, if the pole is in the right half plane, if P1 was negative, it would be unstable. So we didn't consider that case. But in this case, z1 can be either positive or negative. So if z1 is positive, so this means that the pole is in the left half plane, because I have taken 1 plus s by z1. Okay. We will get a response like this. Okay. And what is the horizontal displacement? What is the advance in time? 1 by z1. Okay. And if z1 is less than 0, that is right half plane, then I'll get something that goes the other way. It's terrible. In fact, you're supposed to feed back the signal in one direction. It initially goes in the wrong direction and comes back to the right direction. So it's quite bad. Okay. So the displacement again is 1 by Z1, but this time it's a delay. Okay. So if you have a right half plane pole, it degrades stability. That is again kind of clear from this. It introduces a delay, it goes in the wrong direction and so on. And if you have a pole if you have a 0 in the left half plane, it improves things. So in fact, maybe you can even think of it as a way of improving the performance. Let's say you have certain delay because of some pole, then you can improve it by putting an advance because of a 0. Okay. Maybe you won't be able to compensate it exactly, but you'll be able to compensate it at least partially. Okay. So that's I think you've heard of the term pole 0 compensation. That's the idea there. You add a 0 and maybe you will modify the pole a little bit also, but the net effect of 0 and the pole should be such that the delay is smaller than before. Okay. And the right half plane 0 is definitely bad news. Is it okay? Ringing? No, I'll show you what the effect is. So actually exact response depends on the order of the system and so on. You have just this one, it's still a first order system, so you will not see ringing. You will either see something that is stable or something that is not stable. You'll only see exponential type of responses, right? So only if you have multiple poles and if you have complex conjugate poles will you see ringing. Or what I normally call ringing is something like this. Okay. So if I have something like this or something like this, I would not call it ringing. This is unstable, but it's not ringing. Okay, so to summarize, additional pole, it causes a delay, and the amount of delay is approximately 1 by P2. Okay. I say approximately because it's not like the curve is uniformly delayed. In the initial part, it is some exponential, but in the long term, it looks like a delay. And additional 0, it's again a delay of minus 1 by Z1, or I should say perhaps. So see, here I have chosen the convention so that if P2 is positive, it's in the left half plane, because we are only talking about left half plane poles. Okay. So here the delay is again minus 1 by Z1, or maybe I should say, yeah, I'll say 1 by Z1. So if Z1 is negative or in the left half plane, then we will have an advance. Okay. Maybe to avoid confusion, I'll write it separately. That's probably best. So if it's a right half plane 0 of magnitude Z1, it's a delay. And if it's a left half plane 0 of magnitude Z1, it's an advance of 1 by Z1. Okay. So you can compensate the effect of poles by using a left half plane 0. Okay. Now we can do the exact analysis and see what happens. Exact analysis meaning analysis in the frequency domain. The part we discussed so far is clear, the effect of poles and zeros. So, I mean, you should know that, yeah, what takes you towards instability and what drags you back towards stability. Okay. So let's analyze the case with one pole. Again, we'll look at our prototype feedback system, which has a feedback factor of 1 over k. So what's the closed loop gain? With this being the transfer function of the so-called integrator. So this is a convenient form in many cases. Okay. So what is GH in this case? G is the forward path gain. So GH is simply this whole quantity divided by k, right? So the closed loop transfer function is k 1 by 1 plus the reciprocal of this whole thing. Okay. Okay. So you end up with a second order response instead of a first order response that we had earlier. Now again, whenever you evaluate something like this, which is an extension of an earlier case, you should do a sanity check to make sure that the answer is right. So what's the boundary condition here you can use to check that? If P2 is infinity, it should go back to the earlier case, and it does, right? So this term vanishes if P2 is infinity. So what can you say about this? We have a second order system, so what about it? Like, how do you make any judgment on whether this is a good thing or a bad thing, or what really happens in the time domain? So you can calculate the damping factor or quality factor to see what happens to the step response. What was the step response of the closed loop system before? That is, without P2, what's the step response of the closed loop system? Unit step response of the closed loop system? Ramp. Of the closed loop system. It's an exponential. And what is the steady state value of the exponential? K. So unit step response, it is K, right? So what is it going to be here? That's the question, right? So it can do one of many things. It can do this, it can do this, or it can do something in the middle. Okay. So the second order system is characterized by its natural frequency, omega n. What is the natural frequency of this? And the quality factor, or maybe I'll call this omega p. Okay, omega p and qp. What is omega p and what is qp? So this is omega v by k times p2. It's basically the geometric mean of the previous closed loop bandwidth and the second pole. Okay. And what's the value of qp? Yeah. So these terms are basically, if you reduce the denominator to the standard form, the omega p and qp are the constants in the standard form. Okay. So qp will be omega u by k times p2. Okay. Or if you are more comfortable with the damping factor, what is that? One by two? Yeah. So either ways, I mean, if you want, so if qp is greater than 1 over square root of 2, if qp is greater than half, they will be ringing in the step response. Okay. And if qp is greater than 1 over square root of 2, they will be peaking in the frequency response. So anyway, please figure out what happens in which cases. Figure out the value of P2 for getting no ringing, okay, and for getting no peaking in the frequency response. Okay. No ringing refers to the time domain response, no peaking refers to the frequency domain response. The two are different conditions, so you figure it out. And also figure out the value of P2 for the maximum bandwidth. Okay. We will continue this tomorrow. So, especially figure out if you can get a larger bandwidth than without P2. Okay. So, we have an additional pole, but is it possible to get a larger bandwidth? That is, again, I am talking about maximum bandwidth without peaking. Okay. This is okay. So, the summary is that an additional pole causes a delay in the ramp response. So, and you end up with a second order second order transfer function for the closed loop. And because of the second order transfer function, the parameters are dependent on the second pole. So you can get either critically damped or underdamped or overdamped response. Okay, so you just figure out the constants. Additionally, also figure out what happens if you have a 0. So this is closed loop response with Z1. This is actually quite easy. See if you can make the system unstable by adding a 0. Okay. Okay.